everyone, welcome to this explainer. Today we're diving into something we usually completely take for granted, agricultural irrigation. When we think of farming, we often just think of seeds and soil. But the artificial supply of water to crops, it's an absolute marvel of human engineering. So let's uncover the massive scale, the fascinating techniques, and the hidden mechanics of exactly how we keep the world fed. Here is our roadmap for today. We're going to cover the scale of irrigation, where all that water actually comes from, how we classify these projects, distribution techniques, the quest for efficiency, and finally, the mind-bending virtual water trade. All right, let's jump right into part one, the scale of irrigation. To really wrap our heads around our agricultural footprint, we've got to start by looking at the absolute macro-level scale of the land we're dealing with. 192.2 million. That is the total cropped area in hectares. Just pause and visualize that for a second. It shows the monumental ongoing task of producing enough food to sustain a massive global population. That is an almost unfathomable amount of land that requires constant moisture to actually yield a harvest. But here's the catch, and it's a big one. Out of that massive total, only 67.2 million hectares are actually under irrigation. So doing the math, that means just roughly 20% of the total area, with about 59% being the total cropped area, actually gets the benefit of a guaranteed artificial water supply. The rest of it, well, it relies entirely on the unpredictable mercy of rainfall. Now, you might just think, okay, it grows crops. But the benefits of artificial watering heavily compound. It's literally a fundamental shield protecting entire populations against famine. It lets farmers ditch risky mixed cropping and go all in on cultivating superior, high-yield crops. And it goes way beyond the farm, too. These exact same irrigation structures generate hydroelectric power, they drive broader economic development, and they even secure the water supply for our homes and industries. Honestly, it's the backbone of modern civilization. Which brings us to part two, where the water comes from. If we're watering tens of millions of hectares, we have to ask a super basic but absolutely vital question. Where exactly is all this water coming from? When you picture irrigation, you're probably imagining roaring rivers or giant concrete dams holding back vast blue lakes, right? But the reality of our water infrastructure is actually quite different. The bulk of it is hidden right beneath our feet. It turns out we rely heavily, and I mean heavily, on groundwater. Two wells alone make up a staggering 46% of our irrigation sources. And when you add in other types of wells at 16%, groundwater completely and totally dwarfs surface water solutions. Canals sit at just 24%, and tanks are at a mere 3%. So yeah, we are primarily drinking from the Earth's hidden underground reservoirs. Okay, moving on to part three, classifying irrigation projects. Now that we know the sources, how do we classify the massive infrastructure projects that harvest this water? Well, they're strictly categorized by something called their Culturable Command Area, or CCA. And the scale is vast. You've got your major projects handling massive swaths of land, greater than 10,000 hectares, mostly exploiting surface water. Then you scale down to medium projects, and finally down to minor projects that cover 2,000 hectares or less. But here is the absolute kicker. Despite their unassuming name, those minor projects, we're talking dug wells, shallow tube wells, and small surface lift schemes, they actually do the vast majority of the heavy lifting. They account for a massive 65% of the total irrigation potential utilized. So remember, bigger isn't always the primary driver here. Let's zoom in a bit more for part four, techniques of water distribution. Going from macro-level infrastructure directly down to the dirt of the farm field, we generally see two main philosophies. On one hand, you've got surface irrigation. This is essentially flood irrigation, where we just let gravity do the work to flood an area. On the other hand, we have localized irrigation, also known as micro-irrigation. This is where we use a highly controlled, low-volume, low-pressure piped network to put water exactly, and I mean exactly, where it's needed. If a farmer goes the surface irrigation route, the exact method depends entirely on what they're growing. Got orchard trees? You'll build leveled basins right around them. Planting cotton or sugarcane, you'll dig long, parallel furrows. And for crops like wheat or leafy vegetables, they divide the field into long bays in a process known as border strip irrigation. Now, if we look at those localized methods, the tech gets a lot more sophisticated. Drip irrigation, or trickle irrigation, is incredibly precise. It delivers water literally drop by drop right at the active root zone. And the coolest part, it uniquely allows for fertigation, meaning you can pump liquid fertilizer directly through those same drip lines. On the flip side of localized systems, we have overhead sprinklers. Now, they're definitely effective, but they come with really expensive initial setup costs. Plus, because they spray water into the air under high pressure, they have the potential to waste a lot of valuable water through evaporation. We also categorize these systems by how the water physically reaches the land. We contrast gravity-fed flow systems drawing directly from a river or dam against mechanical lift systems. Lift irrigation becomes totally necessary when your water source is sitting at a lower elevation than your farm, which means you have to pump it up. A prime, incredible example of this engineering feat is the massive pump system used in the Indira Gandhi Canal in Rajasthan.
All right, on to part 5, the quest for efficiency.
As we zoom in to the very roots of the plant, we hit a really challenging scientific roadblock regarding water waste. When it comes to conservation, our ultimate goal is to get this mathematical ratio as close to perfect as possible. Irrigation efficiency is strictly defined as the water actually stored in the soil depth inhabited by active plant roots, divided by the total water applied by the system. Basically, we want every single drop we apply to be directly slurped up by those roots. But tragically, hitting that 100% efficiency mark, it's practically impossible. Why? Because we're constantly fighting a lack of perfect information. We simply cannot accurately estimate the exact quantity of water needed to recharge the soil root zone depth at any given moment. Add to that, we just lack valid real-time data on the actual depth of those active roots underneath the soil. It's like trying to hit a moving target while blindfolded. And finally, part 6, the virtual water trade. Let's zoom all the way out now. We're moving from the microscopic root of a single plant to the massive scale of the global economy for a true paradigm shift. Introduced by Professor Alan Back in the 1990s, the concept of virtual water completely reframes how we think about agriculture. It suggests that agricultural commodities aren't just food, they are physical containers of embedded water. Because every crop requires water to grow, that water is essentially virtually inside the final product. What this means is absolutely wild. The international shipping of agricultural products is actually a massive, invisible global water trade. When a country exports a crop, they are quite literally exporting their own domestic water resources to the buyer. To make this highly abstract idea completely tangible, when a country chooses to import 1 single ton of wheat instead of growing it domestically, it saves approximately 1,300 cubic meters of its own real indigenous water. Think about that. Trading food is literally a massive strategy for national water conservation. So I want to leave you with this final thought to ponder. When we trade crops across international borders, are we really just trading invisible oceans of water? As we look at the immense physical infrastructure we've built to move water to our crops, we've got to recognize the invisible infrastructure of global trade too. Every bite of food you eat, whether it was grown locally or shipped globally, connects you to a vast invisible ocean of traded water. Thanks so much for joining me on this explainer, and keep questioning the hidden systems that sustain our world.